So we're going to talk about electrochemistry and particularly about galvanic cells. Remember that electrochemistry is the interchange of chemical and electrical energy. So we're transforming energy from one form of another. The way we're doing this is you're moving chemical energy to electrical energy. Has to do with the redox, obviously, because redox reactions involve electrons scooting around. That's our primary vehicle. Okay, there are two processes that we're going to talk about. The first one is the generation of an electric current from a spontaneous chemical reaction. And you know this better as a battery. A battery takes chemical energy from a chemical reaction and transforms it into electrical energy because it moves electrons across a wire. The other thing that we are going to talk about in a couple of days' time is electrolysis. And electrolysis is the opposite, and that is taking electricity and forcing a chemical change. All right. Now, galvanic cell is otherwise, chemists can never just have one name for something. They have to have 47. A galvanic cell is a battery. And another term for a galvanic cell is a voltaic cell, named after Mr. Volta. Did you know that? No. No. Okay, I talked about this yesterday. And I talked about notes on I gave you notes on how to balance. Please be aware that the YouTube videos and pencasts can be found on the Unit 17 webpage underneath Notes. And the pencasts are under Files. And they are all PDFs, so you should have no problem opening. And the YouTube videos are under Links. Take advantage of it because I go kind of fast today. Here is a really bad picture, didn't copy well, of a galvanic cell and its components. There's some memorization that has to go here, on here. Make sure that you memorize. Okay, in its simplest form, in the first battery, were just two compartments, two beakers. And there was a liquid portion, a metal electrode, a wire that connected to another metal electrode in a liquid, and something called a salt bridge connects them. All right, in this particular galvanic cell, we have a zinc electrode, and in the liquid portion of the beaker, there are zinc ions and sulfate ions. And then in the other compartment, the copper electrode, solid copper, and it is being bathed in a solution of copper 2 sulfate, and so it is being surrounded by copper ions and sulfate ions. A galvanic cell has a spontaneous flow of electrons. All right, now here comes the memorization part. The two compartments are termed the anode and the cathode. So here are some memory hooks for you. An anode, I always picture it on the left. I'll always do that for you, but somebody will try to trick you up. So you need to be able to identify the anode by what's going on. At the anode, oxidation always occurs. An-ox. Here you go. Here is an-ox. So oxidation always occurs at the anode. What is happening when something's oxidized?
Increasing
It's losing the electrodes. The oxidation number is increasing across the arrow. At the cathode, which I will always picture on the right for you, this is the place where reduction occurs. Red cat, get it? Oh. Red cat. Here's some more cat-based stuff. Look how fabulous this is. How long did it take me to figure all this out? The cathode is positive in a galvanic cell. Look at that right there. Positive. The cathode is positive in a galvanic cell. Here's my personal favorite. Fat cat. Electrons always flow from the anode to the cathode. Get it? Get it? From the anode to the cathode. The cathode, because it's a fat cat, gains mass. All right, I cannot believe that people are just absolutely amazed by all my memory hooks.
It's not your bad.
It is my best.
Vice President Torres' eye is better.
All right, Vice President. Okay. All right.
Yeah, I still like cats or something.
Okay, I'm so sorry. This is the only way for like the first my entire undergrad career that I figured this out. Okay, fat cat, red cat. Okay. Okay. All right. You think you're all that? Turn around. Turn around right now. Don't look at your nose. Just turn yourself around. Turn yourself around. Where is in what compartment would the atoms be gaining electrons? Cathode. Okay. And which electrode gains mass?
Cathode.
Right.
The fat cat. Oh, pardon me. So where do the electrons start out?
Anode.
And they flow to the
Cathode.
Okay. Yeah. You diss my little memory books all you want. You do not know that from anywhere else. You just memorize them. So the electrodes always go from the anode to the cathode. All right. Now, let's talk about this equation and what's happening here. You have the zinc electrode, and so that is elemental zinc. And you have some zinc ions and some sulfate ions. What's occurring at the anode?
Oxidation.
Oxidation. So you have a loss of electrons, is that correct?
Yes.
Yeah. So the zinc is going to the zinc ion, and it's giving up 2 electrons. So the zinc in this piece of metal is being eroded away, and it's throwing zinc ions into the solution. At the same time, it's pumping out electrons over to the cathode. Is that correct?
Wouldn't it be giving electrons to the sulfate?
No.
Then where do they get the -2 from?
They came with -2. Remember, zinc sulfate would be this, and when it ionized, it would be like this.
What is the salt bridge?
What is the salt bridge for? Hang on for just a second. Okay, so this is the oxidation portion of this fun. Now, over here in the cathode, what's occurring? It's gaining electrons. So these copper 2 ions are are gaining the electrons that are coming to the metal copper electrode, yeah? So they are joining onto the metal electrode along with 2 electrons and forming elemental copper. So over time, what happens to the size of the anode's electrode?
Decreases.
And the cathode's electrode? Decreases. It increases. Okay. Now, over time, what happens to these copper ions? They go bye-bye. The concentration of the copper 2 ions in the solution will decrease because they're forming elemental copper and attaching themselves to the cathode. Got it? And the zinc, elemental zinc, is making zinc ions, So we're going to have a really large concentration of charges in each one of these components. That does not make for a nice flow of electrons when you have charged compartments. So we use a salt bridge to attempt to make the compartments as neutral in charge as possible. So on its own, the solution at the anode is becoming positive. Okay, to counteract that positive charge, the salt bridge will give an anion into the compartment. Okay? So it will give, so the cations will join with the anions and be neutralized. You get how that works? Yeah, I forgot it was Tuesday. Maybe I should wake you up by talking about tornadic activity. Okay, in the cathode, there is an overall negative charge because these positive ions are going bye-bye. And so a cation from the salt bridge would be released to keep this compartment relatively neutral. So what is your takeaway thought process on what a salt bridge is?
Neutralizing.
It's a source of ions designed to make the compartments. Yep.
The battery usually runs out because of the salt bridge or because of the ions first?
Well, I guess it could do, in actuality, what ends up is it gets to equilibrium. Give me a minute, we'll talk about cell potential, and then that's really what happens. But I guess you could have salt bridge failure, or you could have this electrode totally disintegrated.
So you can buy a battery and it just can be bad because the salt bridge is screwed up?
This is an elemental one, the ones that you're using, like a Duracell or dry cell technologies. This would be one that you could make in chemistry. I mean, they're all chemistry, but
Dry cell is just magic.
dry cell is just magic. It's made out of paste. Okay, so I think we have finished everything we need to talk about on this page. Okay, everybody's taking physics?
Taking.
No.
Taking?
Yeah.
Y'all didn't take physics?
Nope. Yeah, it's not hard.
It's not hard.
Yeah, but
Oh, look, see this? Yeah.
but everybody knows this. All right, except people who have not taken physics, so I will explain. All right, at the anode, oxidation is taking place and electrons are lost and they're just hanging around. No, they're not. They're being drawn through the wire. So this is the anode, this is the cathode. Yep. All right, so the electrons are moving in this direction. Okay. They're being pulled through the wire. This pull or push is called an electromotive force. And what it is a difference in charge. People who've taken physics know what I mean, huh? A charge potential. Everybody knows when you draw your circuit, you draw your battery like that. Everybody there? Yeah. All right, same thing here. You have a difference in charge, which is a potential difference that we call the cell potential that you know as voltage. Okay. Voltage is the push or pull of electrons. Okay, electromotive force is the term I always knew. The unit for the volt is the unit for this is the volt. The volt is defined as 1 joule of work per coulomb of charge. Okay, this will be important in a little while, not quite yet. All right, Get out your pink sheet or your white sheet of shame. Because you're supposed to, you know, I spent $1 million or some.
Because the pink sheet's on.
Because look, it's on cardstock, it had hole punches, and then you lost it. All right. So, pretty much every redox reaction that we're going to encounter has been chronicled on this wondrous sheet for your enjoyment. It's called the standard reduction potential, and it has to do with aqueous solutions at 25 degrees C. Okay. All of these are in terms of reduction. Get it? Look, all of them are gaining electrons. You know that you can't have just reduction, reduction, reduction. It has to be balanced with
Oxidation.
oxidation. If you found you had a couple of electrodes and one was the anode where what's occurring?
Oxidation.
Oxidation, and all of these were in terms of reduction, what would you do?
Flip the arrow.
I would just flip the equation. What would you do with the standard cell potential in terms of voltage?
Flip the sign.
You would flip the sign as well. That's it? Yes?
All right, cool.
Okay. So if you need oxidation, you're going to reverse the equation and the sign. Please note that the cell potential, otherwise known as the voltage, is an intensive property, and so it does not matter the amount. It's independent of the amount, and that will be important in just a moment. Okay, so far so good? Okay, here's one more thing to notice. The higher the cell potential, the higher the voltage, the more likely this equation will occur. So fluorine, you know, would be very happy to gain some electrons, yes? So it has the highest reduction potential, while little lithium is very interested in giving away its electrons, so it has a very low standard reduction potential. Good? Keep these by you at all times. Okay. So here we are. The half reaction measures the tendency of a chemical species to acquire electrons and be reduced. They decided to measure it against a standard cell potential that is 0. And so they just decided that hydrogen would be 0. And then they measured them relative to hydrogen. Please note that all of these standard reductions are at standard state, which I'm going to tell you for the final time, is at 25 degrees C, 1 molar, and 1 atmosphere. All of these are reductions. Okay. Now, every reaction has its own cell potential that reflects the electrons moving from the anode to the cathode. This is how you figure out the E cell at standard conditions for a reaction.
What is that symbol next to it?
Well, it's supposed to be an cursive E. I don't know what happened.
That's cell potential.
Yeah. Okay. So you have to decide which element is oxidized or reduced using the standard reduction potential table. Remember, the species with the highest standard reduction potential gets to be reduced. Write both equations as is from the chart with their voltages. Reverse the equation that will be oxidized and change the sign of the voltage. This is now the oxidation potential. Balance the two half reactions. This is huge. Please pay big attention to this. Because it's an intensive property, you do not multiply the voltages when you balance the number of electrons that move around. Add the two half reactions together and add the voltages together. Okay. Here you go. Consider a galvanic cell based on the redox reaction here. So we have, this is a net to ionic equation. We have iron 3 ion plus elemental copper, making a copper 2 ion and a iron 2 ion. Here are the half reactions that I just copied off of your standard reduction potential. Based on these, which one of these will be reduced and which one will be oxidized?
Iron.
Iron will be
Reduced.
reduced and the copper will be
Oxidized.
oxidized. Okay. So I'm new at this, so right this moment, by the way, this is a 2. Right this moment in time, I'm going to rewrite this. All right, and I'm going to switch this around. And I'm going to switch the sign. So the E cell for this particular reaction is 0.43. Okay, here, write yourself a reminder. All galvanic cells have a positive. Okay,
Wait, I thought it would be, you just multiply the top by 2.
hang on. A positive E cell.
What concentrations?
Okay. All right, so here is the cell potential. Now I have to balance this redox equation. Is it balanced now?
No.
Now, 1 electron here, 2 here. So I'm just going to multiply this by 2. Am I going to multiply this by 2?
No.
No. So the balanced equation would look like this. So what this is saying is this reaction has to run 2 times for every time this reaction runs. Got it? Okay, you need to turn your paper around. Let us draw what we see. Let us sketch a galvanic cell. I'll spot you this part. Draw wherever you want. What's on the left side? The anode. And the right? Okay. So I need a piece of metal here and a piece of metal here. I need some liquid. And I need a wire. Yes.
Does it matter or not whether the metal is completely submerged in the liquid?
I suppose it would be more efficient if it were for surface area, although people draw it this way. And I need a salt bridge. Okay, now it looks like I have 2 giant eyeballs. Thank you. 2 giant eyeballs and a frowny face. Okay, I need to know what happens at the anode.
Oxidation.
Okay, and in our scenario that we have just done, that would be the copper. All right, so this is going to be elemental copper, yes? A copper electrode. And in the solution, there will be copper ions. Okay. So the copper ion, the electrode is losing electrodes and sending them through the wire and forming more and more copper 2 ions. At the cathode, where the reduction is occurring, what's happening?
Iron.
Iron 3 is gaining an electron and becoming iron 2. Yeah?
So it doesn't matter which one you start with, copper or iron? Like, because on the other one you started with with zinc, and then went to copper, this is going...
That's because it's a different scenario. At the other one, the copper was being reduced.
Yeah,
In this one, it's being oxidized.
So any transition metal can just be flip-flopped like that?
Not any.
What else? Like copper?
It depends it all depends on what your what your standard potential says. So here is the copper, whoops, here is the copper here. If I have a metal like silver that has a higher potential, then copper is going to be oxidized and the silver will be reduced. However, if I have tin, the copper will be reduced and the tin will be oxidized. Okay. Now, I have a question. What's in the liquid? And? No. 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 Well, oh yeah, maybe. We don't know what the anion is.
I am.
Come on. I know you're tired. You need a really good clap of thunder to get you.
Scared.
Well, here comes some. That's very nice. Okay, and here are the ions. Please recall that these are ions that are in solution. You need a piece of metal to serve as the electrode. You need a piece of metal to take the electrons and put them near the ions. What are you going to use?
Fe plus 2. What is that?
Platinum. You're going to use an inner metal. It's not going to react with the iron ions, but it will act as a conduit for the electrons. So if you do not have, as part of your oxidation or reduction equation, a metal that can serve as an electrode, you have to put in an inner metal electrode in
You
there.
just use platinum every time?
I do.
Isn't platinum expensive?
Yes, that's why I use it, because I am all that. Everybody else can use some other dumb base metal. I'm
Pulling out your
What are some
galvanic
other-
cell.
hanging out my
What are some
galvanic
other-
cell.
What are
What
some
about
other
titanium?
metals?
Yeah, I don't think titanium is particularly,
What about manganese? That's the.
manganese,
What's the W?
tungsten. Okay, back on this. Now, here we go. Got this? Everybody's with me now? All right, now every time I talk about a galvanic cell, am I going to have to stop and draw a picture?
No.
No, that would be a waste of time. So there is a shortcut method called the line notation. And it's a way to describe a galvanic cell so that all of us understand what you're talking about without having to draw a picture. Okay. So if we take this particular cell in mind, this is how we do a line notation. On the far left side, we're going to put the anode electrode that we decided was copper. Then you're going to draw a line denoting that it is interfacing with the aqueous solution at the anode, which is the copper 2 ion. Then we know that that is separated by the salt bridge, and we'll have 2 slash lines for the salt bridge. And then we need to talk about the ions that are in the solution at the cathode. There are 2, and I'm going to put them in the order in which they are work. Here's the reactant, here's the product. And then I want to denote that it is in a solution that is bathing the electrode that we decided was platinum. Well, look, that is a lot easier than drawing a picture every time I turn around. Yes? Uh-huh. Okay.
So you have to use the platinum
If there is no solid metal to use.
okay.
Okay. This picture, this line notation, and these equations make up the complete description of a galvanic cell. The complete description of a galvanic cell has to have the cell potential, which you know is positive for a galvanic cell, and a balanced equation. You have to draw the picture. You have to name the cathode and the anode, and you have to give the line notation. Okay, I showed you one. Now you do one. Really?
Practice?
Yeah, yeah.